As a system goes through phase change, its temperature stays the same. However, the entropy actually increases because now you're heating it up, you're adding more energy to the system, and therefore the molecules will begin moving faster, the electrons are moving faster, and so the chaos is increasing. So the entropy changes for reversible phase change is just another way of saying the entropy changes for a system that's going through phase change and is at equilibrium. So while the temperature remains constant, there are a couple things that are true because it's going through equilibrium, or it's in equilibrium. So delta G is going to equal 0, and K, our KEQ value, will be 1. Our value for S, our entropy, our delta S, is going to change though, because we're adding more energy. Heat is being transferred. And we can calculate this delta S using the formula Q over T, where Q is the heat transferred and T is the temperature at which the reaction occurs. Q will be positive if it's an endothermic reaction and negative if it's exothermic. And we're always going to use it in Kelvin. We're always going to use the temperature in Kelvin. Q will be in joules per mole. So our units for this, or for S, are going to be joules per mole Kelvin. So unlike delta H and delta G, S has a temperature in its definition. And a change in S will differ based on the initial temperature. You have to take the initial temperature into consideration. And the best analogy for this is if you have to sneeze. If you're in the middle of a crowded city, say New York, or, well, let's say New York. You're in the middle of a crowded city. Taxis are flying by, people are rushing past you, and you let out a huge sneeze. It doesn't matter how big it is. You're not exactly going to add to the chaos of that situation. You're not exactly adding to the chaos on the street. But let's say you're in a library. Let's say you're in a college library just before exams. And you sneeze, you're going to add more chaos to that library because there's less to begin with. So it's very important to note the temperature at which a reaction occurs. Now, if we're at favored conditions, when we're at 1 atmosphere and 25 degrees Celsius for the surroundings, that means that Q would equal delta H. So this can be rewritten for delta H. So it would be delta S equals delta H over T. If we were going to calculate the entropy of the surroundings, well, this entropy has to go from or come from somewhere, and therefore it would be the inverse of this. So this would be the entropy of the system. If we took the negative of this number, we would get the entropy of the surroundings. And again, our units will stay the same. It's going to be joules per mole Kelvin. You would assign signs, so positive or negative, to delta H based on whether or not it is endo or exothermic. Again, endo will be positive and exo will be negative. So let's say we're asked to determine the entropy of the surroundings given two reactions. Antimony is retrieved from ores depending on what the composition of the ore is. If the ore contains sulfur, we use iron to reduce the sulfur out. To take the sulfur out. If it contains oxygen, we use carbon to pull the sulfur out, leaving us with just antimony. We're asked to calculate the entropy of the system, of the surroundings for each of these reactions. So we're given delta H for both of them. And the units here are a little skewed. They should actually be in kilojoules per mole. Remember, when you're given a delta H, the units will often be in kilojoules, but it also is per mole because it's per mole of this balanced reaction. So I can go ahead and put that in there. So for the first one, as this reaction occurs, we have 125 kilojoules per mole of heat transferred. So our formula again is delta S equals delta H over T. And it's the negative because we're talking about the surroundings. So that heat has to be transferred somewhere, or the entropy has to be transferred somewhere. It's being transferred into the surroundings. So I'm going to actually solve both of these as we go through, since it's asking for calculate the delta S for each reaction at 25 degrees Celsius in 1 atmosphere. So I'm going to go ahead and do that as we go through. I'm going to do both, so you can follow along as each one, or you can pause me and see if you can figure it out for yourself and then come to an answer. Since both reactions are occurring at 25 degrees Celsius, 25 plus 273 is 298, so we have 298 Kelvin. We have to plug in delta H for each of these. And since the first one is an exothermic reaction, we made sure that the 125 was negative. And since the second one is endothermic, we made sure that one is positive. When you divide these out and then make sure you take the negative of each one, you come up with 0.419 kilojoules per mole Kelvin for the sulfur antimony, and for the sulfide antimony, and negative 2.61 kilojoules per mole Kelvin for the oxide antimony. This isn't as neat over here, 0.49, so let's change it into just joules, because on any table that you might be given it, it's going to be in joules, because they won't give you a decimal point like this. That's kind of hideous. So if we multiply this by 1,000, we end up with 419 joules per mole Kelvin. So let's wrap this video up by doing a summary of all of entropy before we get into free energy, which will be the subject of the next video. If delta S is positive, there's more disorder in a system, whereas if delta S is negative, it's more ordered. The universe favors the production of more chaos, so therefore delta S's are more likely to occur. So this can determine whether or not something is spontaneous. There is many things that go into determining if something is spontaneous, but a positive delta S is a good sign that a reaction will be spontaneous. So there are a couple ways to determine if something will have a positive delta S. Anytime you go from fewer moles of a gas to more moles of a gas, that will be a positive delta S. Anytime you have a phase change that goes from a solid to a liquid to a gas in which there's less condensed matter, that will be a positive delta S. And anytime something goes from becomes less dense, it's less dense, that will also be a positive delta S. And again, if you have a positive delta S, that is a good sign, or one of the things you can say that will justify why a reaction is spontaneous. Oh, also, anytime you go backwards in any of these cases would be a negative delta S. So anytime you go from few moles to more moles, that would be a negative delta S. Oh, sorry, just made a mistake. Anytime you go from few moles to more moles, that's a positive delta. And anytime you go from more to few, that'd be a negative delta S. My apologies. Through the magic of editing, you might not see this. So to see this in action, let's consider the reaction between hydrogen and oxygen to produce water. It's a very spontaneous reaction and happens very quickly. If we know the delta H of the reaction, and it's negative 483.6 kilojoules per mole, we can predict, what would we predict delta S to be? Well, we're going from 3 moles of a gas to 2 moles of a gas. So we're going from 3 to 2. I would predict that we'd have a negative delta S. And if we look, it actually does have a negative delta S. Delta S in this case, delta S of the system, is negative 88.9 kilojoules per Kelvin mole. Let's say if we wanted to see how the universe's chaos would change, or at least the surroundings for this system after it goes through this reaction. We could calculate that if we knew the delta H for the reaction, and we do. So we can figure out how this is going to affect the surrounding around it. So first, let's figure out the delta S for the surroundings. Well, if delta H for the system is a negative 483 kilojoules, well, the first law of thermodynamics states that that energy must be transferred from the system to the surroundings. So the positive value of this would be the delta H of the surroundings. And again, the formula for calculating delta S is delta S equals delta H over T. So we go ahead and plug in the delta H for the surroundings. And then temperature, let's assume this reaction is occurring at a comfortable or normal temperature of 25 degrees Celsius. So that's 298 Kelvin. When you divide all that out, you get that the delta S, or the entropy of the surroundings, is 1.62 kilojoules per Kelvin mole. If we wanted to see the overall change in the universe, we could add the change in the entropy of the system to the change in the entropy of the surroundings, and that would give us the change in the entropy for the universe. So we simply plug in the values we got. I changed 1.62 kilojoules to 1,620 joules so that I would have units that would make sense. We would see that the change in the universe is actually only minuscule. So even though the entropy change for the system declines, the entropy change for the surrounding is so large that the overall change of the universe is positive. The bottom line is that if a reaction is spontaneous, or a process is spontaneous in spite of a negative entropy change, as long as it is extremely endothermic. So sufficient endothermicity, and yes, that's a real word, offsets system ordering.